I am Nathan Ridgway with Continued Transportation Cabinet. I work in the Highway Safety Improvement Program, which is housed in Central Office, Frankfort, in the Division of Traffic Operations. I'm going to be presenting today on high friction surface treatments in Kentucky, particularly how we're doing them with our HSIP program. And last year we had a project where our network screening identified a county road to be included with high friction surface, and we were able to get that treatment down last year. And Martha had asked us to kind of come and speak on how the HSIP program worked with the local governments to get a high friction surface project out. So that's what I'll be talking about primarily today. I am going to provide some background information. Just before I jump into pavement friction itself, the Highway Safety Improvement Program, core federal aid program, which looks to implement infrastructure projects that reduce fatal and serious injury crashes. And high friction surface treatment is one of those particular projects where we can really reduce those type of crashes in our state. So we've implemented high friction over more than 100 curves and ramps, interstate ramps across the state since 2009. So it's been very effective for us, and we continue to put out projects each year based on our network screening analysis. So, like I mentioned, I wanted to talk about pavement friction itself before I jumped into high friction surface. And pavement friction, by definition, is the force that resists the relative motion between a vehicle tire and pavement surface. So kind of in layman's terms, it, along with other factors, it helps keep our vehicle on the roadway. When I say other factors, we have to, pavement friction itself will help us stay on the road, but there are other factors such as the driver actually turning the steering wheel in a curve. If they're not paying attention, looking at their cell phone, they don't turn the steering wheel, pavement friction. No pavement friction is going to keep that vehicle on the roadway. The fact that the driver maintains the tread on their vehicle also comes into play with pavement friction, and speeding in general. And I've got a couple of example equations of how speed really can be a factor when it comes to crashes and pavement friction. Overall, there's two components to pavement friction: microtexture and macrotexture. Microtexture is the texture of the stone, or the angularity of the stone. The more angular the stone is, the higher the microtexture, and in turn, the higher the friction value. The macrotexture is kind of the overall texture of the roadway, kind of the depth between the aggregate and the binder. Essentially, a lot of factors come into macrotexture, gradation, etc. But these are the two components that make up friction itself. I want to throw this chart in here to kind of show how friction comes into play versus speeding. I think they can see the cursor, right, Martha? You can see the cursor here on okay. So this chart shows how friction is on the y-axis and then increasing speed or velocity is on the x-axis. And just initially, what jumps out to me are the two curves that have the highest friction value exhibit the high microtexture component, but then also how macrotexture comes into play is it's lower than the low macrotexture for friction values at lower speeds, but as speed progresses, you actually get higher friction when you have a high macrotexture in your pavement. So both components are important to overall friction. Initial friction, high microtexture is kind of a big factor. As speed increases, macrotexture becomes more of an important player. But that kind of chart is just there to kind of show how those values interact with speed. In our state, we use limestone aggregate, which is a pretty durable, strong aggregate. We got abundance of that in our pavements. The only problem with limestone is it tends to polish over time. It's a relatively low polished stone value. Again, just to reiterate, as the stone polishes over time, you're going to lose that contact between your vehicle and your pavement surface, so it starts becoming slicker. So your coefficient of friction is reduced. So again, limestone aggregate, highly used in our pavements, but it does tend to polish when compared to some other aggregates. This slide just shows some initial values for our asphalt pavement, and then kind of over time what we've noticed. You know, give or take, these are just rough numbers, but asphalt pavement in general starts out around 0.5 usually for friction, and then over time you can get into that 0.4 to 0.2 range. It can be as quickly as a year depending on if the mix or the stone you got has polished more rapidly than other mixes. High friction surface in turn has an initial value usually of greater than 1 friction. That's what we measured kind of in the field, some of the older high friction surface we have. As it ages, you're still going to have a higher friction value, high friction surface than our initial values with asphalt pavement. So in short, high friction surface gives you a very high friction value, and over time it's going to maintain that friction value. So when I mentioned other factors that come into play with friction, I kind of got to thinking about kind of some equations, how friction interacts with different variables. And, you know, being the engineer I am, I wanted to look at maybe the presenting and how radius and some of these other factors come into play. This is just a radius equation from the Green Book, and you can move these variables around to solve for either one. But I thought it was a good example of showing how you have other factors that can come into play, particularly when calculating friction. So the Rmin value is equal to the radius of the curve, the minimum radius you need, depending on the other factors. Velocity can be considered speed of the vehicle. Emax is your super elevation / cross slope, and your friction max is just friction. When I look to try to solve for some of these, just to make some examples for this PowerPoint presentation, I wanted to try to just, in my mind, what made sense. You know, first example I wanted to do was say, well, if we didn't have cross slope and we had a very low friction value, for our rural 2-lane roads, typically our speed of our vehicle is 55 miles an hour. What would be the minimum radius we would need? So when I did the math, I come out with a 20,167 foot radius would be needed when you have when you just have 55 mile an hour vehicle and zero cross slope and a very, very, very low friction number. So we all know that we're not going to have a radius on our rural 2-lane roads of 20,167 feet. So what I'm trying to say is initially just our speed of the vehicle is very important, or a big factor when it comes to keeping vehicles on the road. Obviously, if everybody was driving 20 mile an hour, that radius would be much more reduced, and we could probably get closer to what is actually existing out on our rural 2-lane roads. But again, speed in general, it plays a huge importance. And if we have a higher friction value, or we can have a higher friction value that would reduce that amount of radius that would be needed. Second example, as I looked, it's like, well, what is the ideal condition for our rural 2-lane roads? You know, sometimes we have a pretty good radius of around 1,000 foot. I kept the 55 mile an hour speed limit. And I said, well, we usually sometimes have like a 4% to 6% cross slope on these roads. You know, what kind of friction value would we need? And it calculated around 0.16. So if you remember back to what those example initial values and age values of friction showed, you know, you can pretty much maintain that when you have these kind of variables. Now, this is not typically the case on our rural 2-lane roads. Most of our radiuses and our roads weren't designed. These were the paved cow paths that we decided the cow paths we decided to pave. I'm sorry about that. And you know, they weren't engineered per se So we usually have a radius, let's say around 600 foot. Most people are speeding on these curves, so I did a 60-mile-an-hour speed limit, or speed, just travel speed. Super elevation of -3, because sometimes they are in the wrong direction. And this calculated that you would need around a 0.43 friction. So on a new pavement, you can usually get that, we're getting around 0.5, but over time, if it drops below 0.43, it's showing that there's going to be some issues with people trying to stay on the road. They don't have as much friction as they need for these certain situations. So, that was just some examples of how I felt, I wanted to present on these different factors that come into play with friction. It's more than just friction. I will say that good to excellent friction will overcome some of these factors. So again, if you throw in a high friction surface that's got friction greater than 1, it's going to be more than enough for even these conditions to overcome these conditions. So jumping into what actually high friction is, high friction itself is also 2 components. You have a polish resistant aggregate that provides your high level microtexture, and then you have the epoxy resin that is essentially the glue that holds the aggregate to the pavement. This is essentially, you consider back to the chart, this is our high macro texture pavement treatment that we have, and you're going to get very high initial friction values, and even increasing speeds you will have that high level friction as well. Calcine Bauxite is our polish resistant aggregate that we use in our high friction surface. Typical high polish resistant values of 70 is obtained, and PSV is polish stone value. It is a measured test in a laboratory. It gets 70 for calcine bauxite. Limestone is 30. The higher the PSV value, the less likely that stone is to polish. So you can see that calcine bauxite is starting out very strong and will resist polishing very well compared to your other aggregates. The other benefit to calcine bauxite is it actually breaks angularly. So when it actually fractures, it fractures in an angular fashion. So it's going to hold your microtexture. That's why we obtain high friction values over the life of the friction surface treatment itself. Don't want to get into too much about the resin binder. Again, it's just the glue that holds it down. I did steal this table from our Florida folks, HFS folks. Thought it represented exactly what you want from your resin binder for friction. 2 things I kind of thought were important to me, at least, is you want something that can cure relatively fast so you can open up the traffic quickly. And then you want something relatively hard that won't shove under traffic, and then flexible as well to resist cracking. So those are some of the values I saw and characteristics. As far as high friction surface and crash reduction, some of our folks that I noticed on the participation list are safety folks such as myself in other states. They will know that you get a very, very good crash reduction factor or crash modification factor from a high friction surface. Nationally, I think the CMF showed that you get 57% for all crash types and all crash severities. Our experience in Kentucky, we got approximately 90% reduction in wet pavement crashes. It's been very, very, very effective for wet pavement related crashes. We typically use high friction surface exclusively on curves and ramps. That's what we screen our network for wet pavement crashes, for curve segments and interstate ramp segments. Now, when I say interstate ramps or parkway ramps, these are ramps that are typically in the loop ramps where you have to make a sharp turn to get off the interstate parkway. We have used them on intersection approaches, not too much in our state. We've tried it out. I did see an application recently that I thought was pretty good. It was a somebody had placed it on a right turn lane at a T intersection, and typically when you have that situation, there's usually vehicles queued across at the stop bar. And I thought that was a pretty good application for intersections. So I'm actually considering that as we move forward as a good application as well for intersections. But the one place I think we placed it was on a place that had a bit of a grade and people were having trouble stopping. I think at a signal. So that's where we tried it, but we haven't had enough reason to try it elsewhere, but we are open to using it for intersections from time to time. Steep grades, we will typically use this more on steep grades than on intersection approaches because really it's more cost effective to high friction down a steep grade where people are having trouble staying on the roadway than rebuilding the road. So that's where we typically use these. We've used them a couple places, but again, not as much as horizontal curves and ramps. And I failed to mention this at the beginning, but HFST can be used on bridge decks. It started out on bridge decks, the bridge deck sealer. I think they even used it as early as the 70s and 80s. I think once they started placing using it for certain bridge deck sealers, people probably started noticing some crashes that had occurred before did not occur after. So I think people started putting two together on how we could put high friction surface down to start on curves and ramps to start helping people stay on the road in particular trouble places. So it's one thing to kind of talk about curves and ramps and we're going to put them out there, but then when you look at our vast network of roadways, it can be very difficult to figure out where do we place high friction surface for curves and ramps. Where can we place it to get our most return on investment or most bang for our buck? Is very expensive. We don't want to place it everywhere. Kind of an example of that is, in our state, total public mileage, Martha may correct me on this, but we've got about 80,000 centerline miles, 167 lane miles, 67,000 lane miles. State mileage is around 27,677 centerline miles and 63,854 lane miles. So I just took an average pavement width of 10 and multiplied by 63,854. I got square feet, converted to square yards, and got that it would cost around $9 billion for us to do the whole state mileage network with high friction surface. We all would agree that that's not cost effective or a good strategy for using our dollars, and we have nowhere near amount of money to do that. So that's where we get more selective, and we have, like I said, in order to do that, we have to use HSM methodologies with our state. And that's where we do network screening. So I'm not a statistician. I'm not even a safety measure expert by any means. I'm not going to try to explain this to you on how it works. But essentially, people far more intelligent than me figured out a way to use statistical methods to kind of screen or screen for crashes or excessive crashes. It works very well. It targets your most pressing needs, but unfortunately it's still reactive. You have to wait for crashes to occur before identifying locations where to place friction, or in our case, we do screening for friction, we do screening for cable barrier, roadway departure corridors, and intersections, among the others. So I want to show kind of what this screening looks like. This is a scatter plot all the little circular dots are crashes per mile over ADT. I don't think this is always the case, crashes per mile. I think it's a little bit different for whatever you're screening for. I think on this one was a rural parkway, so I think they had to divide that down to per mile versus per foot. But anyways, each little dot represents a segment for crashes versus their ADT. And what they do when they get these plots, they'll do a line of best fit. And that's what's called a safety performance function. So it's just a line of best fit based on your crash data. Any dot that's above the SPF line, that segment or location is having more crashes than the average. So these dots below are having less crashes than the average. So we tend to target these locations above the safety performance function. This is kind of a simplified look at what a safety performance function is. This square dot on the safety performance function, if you had a location that falls on this safety performance function, that location is performing similar to its peers or similar to different sites across the state. The circular dot is the observed period, so the year or the analysis period. So we typically do 5 years. And then what HSM does this empirical base method to correct for the historical average. Don't get hung up on that. But basically it's using statistics to correct and kind of lower these observed periods down for the historical average. I think it even can go up, but I'd have to check with that. But anyways, what we look at, what value we gather and use for our network screening and site selection is this excess expected crashes. So the difference between the EB corrected and the average, we say this location is performing worse than its peers. We take those EEC values and weight them with crash cost. And then we get like a ranking across the state, and we say, we look at the first 0 to 20. We can't do all of those, but we evaluate the worst 20 in the state. And we screen for wet pavement crashes for curves and wet pavement crashes for ramps. So we look at both. And we take that and we start determining sites, and then we'll usually do it like a initial investigation using Street View or photo log, and we'll look at it as kind of the geometry, how the radius looks. Does it appear like the cross slopes an issue, or do we have a bunch of utilities in the way, or trees, or anything that could be an issue with or other factor? Does it have signing? If it doesn't have horizontal signing, maybe we need to look at doing that first. But most importantly, we actually go and look at all these sites that we determine that we want to do friction on. And I feel like this is the most important step anytime you're considering doing high friction surface, is go out and do your site visit. Look for the horizontal signs. If they don't have horizontal signs on the curb, they probably need to be there. That's more, it's a lower cost treatment that may be enough to help the crash problem. Is the super reverse? Can we easily fix the super with new pavement and get a better performer and more cost-effective price? And then, like this picture illustrates that this pavement here at this location, this was before my time. I assumed it was one of those that they were looking at doing high friction. And, as a new pavement, I think they may have had crashes occurring, but you can see there was rutting on this pavement. No matter how friction is going to fix that problem, you need to look at fixing those those issues and before you go down the road of high friction surface, in my opinion. And then this goes back to what Martha's always hitting on me and asking me about is, are local roadways involved? And I will say yes, they are involved in our screening, but not all of them. There's data limitations to that screening. If you go back and recollect on the slide I showed you the SPF curve, you have to have ADT. If you don't collect ADT, we can't incorporate into our screening. That's one of the limitations. I think there's some others as well. But, you know, if the roadway is locally owned but classified as a collector or above, that does get included in our state screening process. So we do target roadways that come up if they come up for excessive crashes on locally owned roads. Which leads to our local project we had last year. County Road 1215 in Daviess County is a locally owned collector road. It was in our screening. Curve 1 was identified as a curve that had excessive wet pavement crashes. And this was the first, I think, local road we've actually had come up on our screening. So we were, I called Mark to see if they were interested, and he obviously was. And, but he had also mentioned that curve 2, just, I guess, east of there, curve 1, was also a problematic curve, and he wanted me to do like another analysis, and we did, and we determined that friction would be a good option for this curve as well. So, we went down the road. We identified this early 2019, and we had it. I think we identified in January or February. We had it, I think, in the letting by April or May, which is pretty good, quick turnaround on this project. And I think it was built at least by October. So very, very quick project to get out the door, and very successful as well. So I'm going to pass this over to Mark. I'm going to shut up and pass it over to Mark and talk about this experience with the project. And that's all I got.
Does anybody have any questions for Nathan before Mark about Roadway? I don't see any questions in the chat pod yet, but remember, you can always put your question in the chat pod or take yourself off mute if you have any questions. Thanks, Mark.
Thank you. Nathan, if you go to the next page. So from a local jurisdiction, Nathan, like he said, he called me early 2019, and unfortunately, we had a local road pop up on their radar, and once he sent me some of the information, we started to look at that road. Veach Road, which is CR 1215, has been on our radar since I've been the county engineer. It's a main road leading from the city of Owensboro to a arterial highway. It goes to a local community college. So it has one of our greater ADTs for the county. And when he showed me, like he said, curve 1, it was not so much on our radar. You may not be able to see very well from the pictures, but that's a pretty rural section of road. You've got fields on both sides, some trees. So when we had crashes, they would get reported, but I wouldn't receive the reports in my office. Very little damage was done to the roadside. They would drive off into a field, maybe hit a fence, but that's about it. So we were very, very aware of curve 2. If you'll go to the next slide, Nathan. Curve 2 actually went into 2 residential yards, one belonging to a local attorney. So I would get a call just about every time it rained, complaining about a vehicle going through his yard. Or before, we had guardrail just beyond this curve. And every time it would get hit, we would get a call from 911 about damage to the guardrail. And unfortunately, anybody that's aware of maintenance of roadways knows that guardrail is very expensive to repair. You just can't go out there and put up new steel. You have to get a contractor. It's got to be up to date, in treatments and so forth. So we were spending quite a bit of money on Curve 2 multiple times a year replacing guardrail. So 8 years ago, after enough calls, we did a audit of this curve particularly, and we started doing some low cost improvements, like Nathan was talking about, maybe a good first step. We removed the guardrail. We flattened out the slopes of the shoulder. We cut several trees, 5, 6, 7 trees to make the roadside more recoverable. We started putting up some advanced warning signs. You'll see from the pictures, there was one large arrow. I think we started with one large arrow in each direction and advanced warning. Then we kind of watched that for a period of time, and crashes didn't decrease, significantly at least. So we went back through, and as you can see from these pictures, we started adding dual-mounted advanced warning signs. We added chevrons. We did some rock on the shoulders, things of that nature, trying to decrease the speed going through the curves so we'd have less crashes. And we saw a little bit of benefit, but unfortunately, just every time it rained or the first snow event, we were getting crashes repeatedly. So 2 or 3 years ago, I looked at doing a high friction surface on our own, just with county funding. And as Nathan said, it's pretty expensive. For the cost of doing just curve 1, we can pave about a mile of county roadway. So it's a pretty significant undertaking for the county, for any county, I think, to do it on their own. So we kind of settled with not doing at that time any high friction surface and just relied on the signs that were out there. So when Nathan called and brought up curve 1, they graciously looked at curve 2 at our request. And thank goodness, it also seemed to be a good candidate for this. So after the news that we could do both curve 1 and curve 2 under this program, it was a pretty simple process. The transportation cabinet, Nathan and his group, pretty much set up the entire project, the bid package. Went out to bid. We got to review the bid documents, the traffic control measures on the county road and so forth. And it was let. And Nathan, you correct me if I'm wrong, but the contractor was very responsive. They made contact with the local government, with myself as far as scheduling. The highway department's local inspectors did the inspection. They did allow me to send out my road inspector to watch this project be done for our local knowledge. So that was great. But it was seamless, quite frankly. No issues, no hiccups from conception to birth. It was a pretty seamless method. So this is what we ended up with. If you want to go through the next couple of slides, Nathan. You can see the difference in color and no issues. Nathan, if you want to pick up the results of the project as far as the data collected.
Yeah, we're nearing the end of the presentation. I just want to reiterate, with this project, working with local governments, I wanted to make sure that I even wrote in the special notes, the contact the Daviess County engineer before working, just so that there's communication at least, because we were administrating the contract, but it's their road. So we wanted to get that involvement as well. So I don't think Mark had many issues with it, but again, you want to add that in there. Before the presentation, I thought I would look at the crash history, and then curve 1 had 16 total wet pavement crashes. So far, we've had 0 on this curve. Now, I do recognize it hasn't been a full year. 2020 is still going on, and we have COVID, so ADT's down, so most likely crashes are down. But again, nationally, we're going to get, or in our state, we got 90% wet pavement related crashes. So I don't expect many future wet pavement crashes to occur on these both of these curves. Curve 2, even with the signing and some of the other stuff Mark had done, had 33 total wet pavement crashes. They have not had any wet pavement crashes so far since implementation. So very successful, I think. So far, should be continued success and in the future. So, in conclusion, again, their HFSTs are very effective at reducing wet pavement related crashes. They're also very expensive. I will say they're not always a silver bullet to do your field visit. Maybe there are low cost alternatives that you can do before going down high friction. And in our state, we consider it as a temporary solution in some cases, particularly if there's a real curve that pops on a radar, it's polished, it's been around for 8 years. We'll put down friction until it gets repaved. And when it gets repaved, doesn't necessarily mean that it has to go back. Maybe when they repave it, they can put some super elevation in and put a polish resistant aggregate on a regular mix and see how that holds up. So it's not always a permanent solution is what I'm getting at. Because I think a lot of times people have concerns with maintenance. And we say, I think there's locations where we identify that, well, we're going to have to probably put that back. But we don't always consider putting it back after it's been placed, so, or replaced. So that's all I got.